Let us discuss about the third applications of conductance measurement, which is your determination of solubility and solubility product of sparingly soluble salts. Okay. So when we are talking about sparingly soluble salt, that the meanings of it is that salt will not going to easily dissolve or easily going to soluble in solvent like water. Okay, and many examples of sparingly soluble salts are known, and most popular examples of sparingly soluble salts are, silver chloride, barium sulfate, lead sulfate, etc. Okay, so among there are many types of sparingly soluble salt, and in this topic we will mainly going to discuss about silver chloride solution. Okay, because this is easily we can obtain this one easily, but the cost of this one is slightly high because silver is there. So even we can use barium sulfate also, or let's sulfate, okay, to carry out an experiment, okay, to find out their solubility. So actually, why we actually use the conductometric, or why we prefer the conductometric titration, not titration, conductometric measurement to calculate the solubility of the sparingly soluble salt solutions. The main reason is that if you going to prepare their solutions, let's suppose silver chloride solution, okay, in water, okay, let's suppose we add some silver chloride here, okay, silver chloride. So because they are not easily soluble, so that's why they will generate a very little amount of ions. That means the concentration of this solution is very small. Okay, the concentration of sparingly soluble salt is very small, always. Okay, always very small. If the concentration is very small, then we cannot use the chemical techniques or chemical method. We cannot use chemical method to calculate their concentrations, because there are some limit, or there are some limitation of chemical methods. If the concentration is not up to that limit, then it will not going to detect, or you cannot calculate their concentrations. Okay, that's why. But in case of if you use a chemical, or not chemical, actually the conductance measurement technique, then it can able to measure the the solubility or the concentration of the that type of solutions. So mainly the experimental method of that experimental setup is like just a very simple setup. Okay, what you have to do, you have to just prepare the solution of that sparingly soluble salt. Let's suppose, okay, before preparing the solution, what you have to do, you're going to prepare that solution in some solvent. Let's suppose that solvent is water, and let's suppose this is your conductivity water. Okay, so what is the meaning of conductivity water? That means that water has some impurities. Okay, that impurities will going to increase the conductivity of that water. That means let's first suppose take some water which are impure, and we can have there, what we can have there, we can calculate the specific conductance. We can specific conductance by just simply putting two electrodes inside, or by inserting two electrodes inside that water. Okay, so we can calculate the value of kappa. Okay, so value of kappa by using normal setup. So let's suppose the K1 represents your specific conductance of water. Okay, so this is not deionized water, it is ionized water. Okay, impure. So we can have this value, and we can calculate. Okay, so after obtaining this value of that means specific conductance of water, what you can do, you can just uh, put the silver chloride inside this solution, or you can even prepare the silver chloride solution in some um, beaker, and that solution can be poured here. First remove this water, then pour this solution. Okay, you can do this way also, or you can even just add silver chloride in this water and just stir this one, then put insert that two electrodes and try to calculate the specific conductance. Then let's suppose the value of specific conductance for the solution of silver chloride. That means the conductance will be what? Conductance will be due to the impurities present in the water plus the ions which will going to produce from this salt. Okay, will be, let's suppose this is K to represent your specific conductance of that silver chloride solution. That means the specific conductivity will be slightly higher than this. K2 will be slightly higher than this one, because additional some silver positive and Cl negative will be formed inside this solution, and they will going to contribute to the conductivity of that solution. Okay, so the net, that means the net, or we can say that the specific conductance of that solution due to only for the silver and chloride ion will be what? Let's suppose this is Z. Z represent what? The specific conductance only because of silver positive and chloride ion. So what we have to do, we have to subtract K1 from K2, because K1 represent what? The specific conductance of water. So we have to first minus this one, because I think you understand this one. Okay, so and from this K2. Okay, so we can calculate the value of the specific conductance for that solutions because of only because of silver positive and chloride negative ions. Okay, so this is up to this one we have. So now what we have the specific conductance of that solution. Okay, so now, okay, wait, no, okay, so we have that value Z. Okay, so and the unit will be what? Siemens per meter, because the unit of specific conductance we already know that Siemens per meter. Okay, so again let us suppose that solubility. So what is our aim? Our aim is to calculate the specific, not a specific conductance, our solubility. No? Suppose the solubility of the silver chloride solution is let's suppose X mole per meter cube. If it is your solubility, then what? X mole per meter cube. Moles per meter cube means what? Concentration. That means the concentration will be also your X mole per meter cube. And again, from the definition of molar ionic conductance or molar conductance, we know that the molar conductance is defined as the specific conductance divided by C. Okay, the ratio of these two. Okay, and here we have the value of the specific conductance from that experiment, and that is your Z. We have the value now. We know this value from this experiment. From the experiment we have this value, and concentration we don't know the concentration. Okay, this is X moles per meter cube. So this is your Siemens per meter, and this is your moles per meter cube. Okay, so this is your lambda m. So now lambda m is equal to Z by X. This is your Siemens mole per meter, no, meter square. Okay, per mole meter square. Okay, so okay, so we have this relation. Okay, lambda m is equal to this one. So what is our aim? Our aim is to calculate X. Okay, that is the solubility. So X is equal to your z by lambda m. So we have this value from that experiment, and the unit will be what here, moles per meter cube. Okay, so we have this value, and also we can calculate the value of lambda m. So how are we going to calculate? So for that, go to the next page. Okay, so here you see, if you notice here, we know that actually this is what this is lambda m is. Lambda is your molar conductance. Okay, this is your molar conductance, but the thing is that the solution is what in this case. In this case, the solution is very dilute, because they will going to produce hardly a little amount of ions during the dissolution process. Okay, so that means it will act as a what, a solution which is actually that solution will behave like an infinitely dilute solution. So that means the molar conductance of that will be what, it will be like lambda m naught. Understand it? So that means we can write in place of lambda m naught. Understand? Okay, so again, by using the Coriolis law, we can calculate the lambda m for silver chloride. Okay, and we know that this is equal to silver plus lambda naught. So this is Coriolis law, and using this law we can calculate the value of this one. Okay, so and this is actually known as the value, and this value and this value is already known. Okay, so just put the value, and actually the value is 138.26 into 10 to the power minus 4. Okay, so this is the value. Actually the unit of this one is what, Siemens per mole meter square. Okay, meter square. So we have this Siemens per mole meter square. So you can go to check the unit. Okay, so here that means we have the z from that experiment. We have the value of z from that experiment, and we can calculate the lambda m for the silver chloride by using Coriolis law. Okay, that means we have the tools. Okay, so we can calculate the value of x. X is what, your concentrations, also, and concentration is what, solubility. So we can calculate solubility from the conductance data. Conductance data here, conductance data is what, z. Okay, so by from that experiment we can calculate z, and once we have this value of z, we can have the solubility of that sparingly soluble salt. Okay, because the molar conductance can be calculated by using what, Coriolis laws, because this molar conductance will act as a molar conductance at infinite dilution, because the solution is very dilute. Okay, I think you understand this. This application, the third applications of conductance measurements. So now we're going to discuss about the fourth one. Okay, so mainly we're going to discuss this conductometric gradations, and this is actually fourth applications of your conductance measurements, and this is a very important topic. Okay, so we're going to discuss this in details in next class, but today I am just giving you a brief idea about the conductometric gradations. Actually, when we are talking about gradation, it is like the acid and base gradations. So we're going to use period and that all. Okay, but in case of here in place of that indicator, we're going to use the one electrodes. Okay, not one electrodes, two electrodes actually combined in a setup like this. Okay, so there will be an instrument. This is electrode. Actually there will be some plate. Okay, two electrodes will be there, and they have a fixed distance. Okay, and they are their area of, actually if you zoom this one, then it will be like this. Okay, two plates will be there, and their area will be same, and this will be known, and the distance of this electrodes will also given. Okay, and in that electrodes it will be written uh, actually this is what, this is your cell constant. Cell constant, you can calculate the cell constant if you know the area and the length of this one, L by N. Just cell constant is equal to L by, and the cell constant is actually in all, actually mainly, usually the cell constant is written on the top of that electrodes. Okay, so in the conductometric tradition, what we will do, we'll just there's an instrument. Okay, so there's a digital meter. Okay, a digital actually display will be there, in which we can check their conductivity, okay, or the resistance of that solution. If you insert this electrode in a solution. Okay, so what we're going to do in this conductometric tradition, we're going to insert that electrode in a solution in which we have to do the tradition. Okay, let's suppose here burette. Okay, we're going to add here let's suppose sodium hydroxide, some base. Okay, and here let's suppose HCl. Okay, so we're going to add the base from that burette, and here let's suppose we take some volume of HCl and add sodium hydroxide from the burette. So after adding each drop of sodium hydroxide, we're going to stir this solution, and to mix that solution properly, or to that sodium hydroxide, when the sodium hydroxide will going to fall down from that burette, then that sodium hydroxide will going to react with that HCl, and they will going to neutralize it, a little amount of it. So for that process we have to stir this one to mix it properly. Okay, we have to mix it, and after mixing this one we have to wait for 1 to 2 minutes. Then we're going to take the reading. Okay, take the reading here by pressing or by putting the instrument on. Okay, when we switch on this one, then we're going to get some resistance value here, and also sometimes some conductance value here. Okay, so we have to record that value, and so after adding each drop from that drop of sodium hydroxide, we have to take the readings from this display and just plotted graph. Okay, so we're going to get some graph like this. So we're going to discuss this things. Okay, so about this graph, and from by using this graph we're going to actually get the end point of that acid base neutralization reactions. Okay, so this is actually a type of traditions, but instead of indicator, we're going to use this electrode to indicate our endpoint. So this is a very interesting topic, and we're going to discuss in details in next class. Okay, hope you understand up to this